long as you're extending to Q. Right? So if I Q extend this guy, I just proved on this board Manin's theorem that says there's an identification of the homology with Q coefficients with this space of cuspidal modular symbols. Okay? Let's also writing them as alpha beta, thinking about that as being they take the path map. Okay? So are you guys comfortable with that now? That's the kind of the main point of today, is that modular symbols give us a way to equip these guys. This is the thing we always cared about, the modular forms. And by pairing in duality, you see the same thing. Okay, so it's one is dual to the other. And the modular symbols have a nice concrete interpretation, right? We had all those fairy symbols and whatnot to keep track of cusps and their gamma orbits. Okay, so extend to R. So if you do that, then the R dimension of this S2 gamma, well, the C dimension was G. So what's the R dimension going to be? With a C vector space, and I think about it as an R vector space, what happens to the dimension? 2G. Okay, and well, this was going to be the same thing as the dimension over R, this H1 times gamma R. And then the proposition is that the integration pairing is perfect. Am I speaking good linear algebra for you guys? Do you like pairings in mathematics? Relating vector spaces to their duals? Okay, the integration pairing is perfect. If you don't like it, I'm just going to tell you the conclusion that we need here, which is if you take HOMS from S2 gamma to C, R HOMS of that R vector space to C, this is isomorphic to the space of cuspidal modular symbols for gamma where I tensor up to R. Okay, so does that make sense? So perfectness is what gives me an isomorphism of the one space to the other. And I'm telling you that this space that we wrote down, which is some like almost combinatorial number theoretic, I keep track of cusp and gamma orbits, is encoding everything that I want about a space of modular forms, but strictly speaking it's dual. Okay? So in particular, it tells you that the dimensions are the same. But that's not news to you, is it? If G is the genus, and the dimension of the space of modular forms is... So there's a little... So why is there a 2 there? Well, it's because whenever you have a modular form, you also have the complex conjugate. So there's a complex conjugation happening here between R and C. And I think that's a point I don't want to dwell upon right now. So the moral is that modular symbols are modular forms. Modular symbols are modular forms. Strictly speaking, they are the dual. Okay, that's what I want you to take away from today's lecture. Modular symbols are modular forms. Strictly speaking, the dual. Okay? Let's play with gamma 011 to finish up today. Are there any questions before I show you what this looks like concretely? Feeling good? All right, example. What's the fairy symbol for gamma 011? Did anyone figure this out? Okay, I'll tell you what I computed in preparation for these lectures. I think this is what Sage popped out yesterday too, if I remember right. I think Harris showed us all of the gamma 0 and modular symbols. He asked you to look for a pattern among them, and I started to see patterns there. So there's no even or odd here. Every pairing is free. So those are the matrices that I computed. I don't know, you should probably be skeptical of anything that I'm trying to sell you. So let's do some basic sanity checks. Well, what can we do without trying too hard? We can verify that this guy maps to this guy without thinking too hard. Infinity does go to infinity under the map z goes to z plus 1, and 0 goes to 1 under z goes to z plus 1. So that looks good. Maybe you want to plug into this guy, z is equal to 0. Boy, that's scary. The answer that you get is 2/3. Does that match up? Yeah, I guess this guy is going to go to this guy. Okay? So that's the end of the sanity checks, but you should continue to perform them. What are the cusps? Well, this is a little interesting. You guys know for other reasons, what the cusp of gamma 0 of p is, right? The answer is it's always, when p is prime, the answer is always just 0 and infinity. Okay, but let's see that from the calculation here. So how do you find the cusps from the very simple? Every cusp is represented here, and you take the equivalence relation induced by the parents. Okay, so for example, I have infinity is connected to minus infinity. I would also have 0, but 0 is connected to 1 by the element 2. Sorry, no, cheating. Yeah, it is. It's 0, it's this guy, and then it maps to this guy. Yeah? You just saw that, with the 0, okay? Via this element of gamma 0 of 11. You see that 0 and 1 are identified. Okay, but then this 1 via the 3, where does it go? Well, it looks to me like it's going to be identified with 1/3. Okay, but 1/3 belongs to the 2. Okay, so that means that the 1/3 gets represented to the 1/2. Okay, so if you keep doing this, you see that they're all the others are identified. Okay, so that's the 0 infinity. Okay. Does that make sense? So what is the space of modular symbols M2 gamma spanned by? Is it just 0 infinity? Well, that would be the cusps. We have to consider all the sorts of paths that go between them, right? So let's be a little bit more careful. What was the answer for the M2 of gamma when gamma was SL2C? What was the answer? It was just the 0 infinity, right? Because every other symbol was identified in the quotient because of continued fractions. Okay? So by that reason, well, if we took the gamma orbits of that symbol, that's what you're thinking here also with the cusps. Then that will also tell me all of the possible paths. Okay? So, I mean, we might as well write them all out. They'll be infinity 0, 0, 1/3, all the way down to 1 infinity. Those are all of the possible gamma. So I wrote down every possible combination of symbol. Gamma 0, 0, 1/3, and so on. That's what I've tried to write down here. I'm not going to write down minus infinity anymore. That's only really for the very simple. Minus infinity is the same thing as infinity. Okay? Why are those all of the possible paths of the gamma equivalence? Right? You have to be a little careful. It's not just all the cusps. I want all of the paths between all of the cusps up to gamma equivalence. Okay? Well, if I just do them, this is a redundant set, but is it clear that I've got everything covered? Because I do this one, this one, this one. So if I want to go between number 2 and number 4, I go from 2 to 3 and then 3 to 4. So I just have to write them in order. Okay? So you see the value of the fairy symbol for keeping track of that? Okay. Now we have to decide which of these are equivalent. That's exactly what's provided here with this data. So, for example, what can you tell me about the relationship between this symbol and this symbol? So minus infinity 0 and 1 infinity. Those are going to, right? So that via this element, they are equivalent in the M2 gamma, by definition. Yeah? Okay, so how many symbols do I need to span? Well, at least to me, like I have 1, 2, 3, 4, 5, 6. And I make 2 identifications, or sorry, three identifications among them. So why don't we just pick these 3? And then we'll know that they're equivalent via the 1, 2, and 3 to the other ones. Okay, and then that's it. That's all the gluing relations that we have. So a basis is given by, am I making sense? my favorite version? Okay, great. So what is the S2 basis? This is an M2 basis, M2 gamma basis. What about the S2? What's the difference between the M2 and the S2? No. Start and end at the same place? Okay, so if I have a map from a vector space to a one-dimensional space, I should be getting something which is two-dimensional in the kernel, right? As long as the map wasn't identically zero, which it is not in this case, okay? So can you find me the two elements? Lo and behold, the 0 and the 1/3 and the 1/3 and the 1/2 have the same image in the quotient, yo. Okay, so it's just the 0 infinity that we don't need. Okay? Is that clear? So this is a path that looks non-trivial in the upper half plane. It goes from 1/3 to 1/2 to 1/3. But in the quotient, it looks like a loop. Okay, and you might say, well, all loops are the same, right? Okay, well, in the upper half plane they are, I guess, because it's simply connected. But in the quotient, you don't know, because you're trying to go around some guy, all right? And well, if you believe it, then this is supposed to generate the homology of the x0 of 11. How could that be? Well, okay, I'm just about to erase the dimension over R of S2 gamma. Should have tensored there with R, but oh no, that's already a C vector space. Okay, forget about script regular. Okay, so well, let me write this. Dimension over Q of the S2 Q, S2 gamma. So we just decided that this was 2. Yeah, for gamma 0, 11. Okay, and that's supposed to be related to the genus somehow. And the answer is by the formulas that I just erased. This is 2G. Strictly speaking, you have to tensor up to R, but that gives you same dimensions. So that means that the genus of x0 of 11, which is my x of gamma, is equal to 1. Okay, so here's your donut. They have donuts up there. What's the point of this donut? Well, apparently there's these canonical paths on the donut that generate the homology. Is this concrete enough for you? And how will you label these paths? Well, one of them is labeled 0, 1/3, and the other one is labeled 0, 1/2. 1/3, 1/2, I'm sorry. 0, 1/3. I guess I could have labeled them any way I wanted to. As long as I took a good Z-linear combination of them. Okay? So that is a picture. If you want to, well, I'm going to run out of time quickly here, but you can take the quotient of the upper half plane and try to, I never succeeded at this, maybe you guys have better powers of visualization, but fold it together and see the donut. Okay, so you'd have to take the quotient of the upper half plane. Remember those beautiful pictures we saw yesterday with the triangulations? So you fold these edges together, and then there's some gluing relations, and then magically you get something like this. Okay? I always find that exercise to be hard to do, at least for the SL2Z, I can sort of see how you glue the sides together to get something that looks like a sphere. But this is, do you see how there's a different method to visualize what that quotient looks like? And we're reading it off of this data. Okay, so we started with fairy symbols, which told us the necessary input to compute things like genus. Okay, there's other ways to read off genus directly. But, now, I guess I want to end with the punchline here. What is the modular forms? What are they for x naught of 11? I don't know if Harris did this one, but do you guys know this? This is a one-dimensional space of modular forms, right? Dimension over C, S2 gamma is G. That's the definition of G. Is equal to 1. Okay, so what does that mean? Well, this is the C-span of some favorite modular form F. Okay, what is the modular form F? It's a nice cusp form, F of Z. This This is the one that wins all the beauty contests, right? It has a product expansion, it's eta functions like Amanda told us. This you could, I don't know, you guys like? I think you have to put the Z in order for this to be correct. You guys remember? All right. Amanda told us all sorts of amazing things, but I just rewrote the thing on the top line if you don't remember the Dedekind eta function. So I have everything wrong. What's wrong here? Q to the 11 n squared. No, that's right.
That's good. That's good.
24. Okay. I guess you could expand this out to get a Q expansion. It starts out Q minus 2Q squared minus Q cubed, and so on. You guys have seen this one before? I hope you'll see it every couple of days. It's a good friend, good old friend. Okay, will never fail you. What's the significance today of this modular form F? Well, it is via the integration pairing dual to this pair of modular symbols. What does that mean? That means that if I integrate f of z between these two, along these two paths, that'll give me two complex numbers. And what do those complex numbers tell you? Well, they give you a way to visualize this curve. Well, it's supposed to be an elliptic curve. So let's dually, right, along these paths, if I draw it as a lattice, oh, I can't call them omegas because I had omegas earlier. Lambda 1. So lambda 1 would be the integral from 0 to a half, 1/3 of my f of z dz. Right? So then this is one path, this is the other path, and the quotient gives you the thing that folds up to give you the donut. So these are the periods. Maybe you want to take the right ratio of them with positive imaginary parts. So you can think about, you know, that complex analytic theory of elliptic curves where you relate them to lattices and C. Okay, so is that explicit enough for what? Is there anything else? So everything that you could want to know about the space of modular forms, its dimension, so the significance of the coefficients, all of that. Okay, that's all present in this diagram. So I guess the next question you would have is, computationally, the only thing that we've really seen here is dimensions of things, right? Okay, I produced this function from what? You know, because I told you it was an old friend, but if you look at it again, you're like, well, where did you come from? You just entered the room. How did I know that this was a modular form? And if I replace 11 with something else, how am I going to write down, I don't know, Q expansions that then I could then integrate? Okay, that's a good question. The answer is Hecke operators. Okay, there are natural linear operators on, you take your pick, either the space of modular forms or dually the space of modular symbols. So if I take, they are self-adjoint with respect to a nice pairing. So there's a common eigenbasis, and in an eigenbasis, the coefficients are the eigenvalues of those Hecke operators. So if I want to pick off the third coefficient, I need to know the matrix for the Hecke operator T3, which we got to see some of yesterday. So tomorrow, what I want to tell you is how do you compute Hecke operators on modular symbols? Because if I've done that via the duality, it tells you how to compute Q expansions of the forms, right? And the relationship is given by the integration pairing. Okay? So how do Hecke operators act? Well, it's again a beautiful story of manipulating zero infinity, having things act, continued fractions, very algorithmic. So that's what you get to look forward to tomorrow. Okay, see you then.